Digging Deeper Videos, Section 5.7, Guessing Explicit Formulas. This is Discrete Mathematics, Fall Quarter 2023, and I am the instructor, Charles Wiczorek. Let's consider an identity. For all n positive integer, the sum from I equal 1 to n of I cubed is equal to this explicit formula. At least this is what we're being told. It's equal to n squared times the quantity n plus 1 squared divided by 4. Let's check it. For n equal 5, we'll have the following. We'll plug 5 in for n, and we'll have the summation from 1 to 5 of I cubed, and that will be expanding it, 1 cubed plus 2 cubed, all the way up to 5 cubed. Just a summation of the 5 terms. If we bring out the cubes and add them, we have a total of 225. But let's look at the explicit formula. Let's substitute 5 for n. We'll get 5 squared times the quantity, 5 plus 1 squared, divided by 4. Well, that's 25 times 36 divided by 4, 25 times 9. And the final total is 225. So that agrees with what we got on from the summation. It worked. But this is an example, it's not a proof. And let me ask you a question. What proof method would you use to prove this identity? Yes, mathematical induction. We know how to prove the identity, but how are identities like this created? Let's define a notation for a power series from 1 to n, and a positive integer, with an exponent k, a positive integer. So it'll look like this. S sub k, capital S sub k, is equal to the summation I equal 1 to n of I to the kth power. Here's an example. S sub 1 is the summation I equal 1 to n of I to the first power, and if we evaluated the summation, we'd get 1 plus 2 plus all the way to n. S sub 2, similar, the summation I equal 1 to n of I squared. And so evaluating that, we'd get 1 squared plus 2 squared plus on and on till n squared. And if we continued like this, we'd end up with k. So let's stop at k. S sub k would be just the sum, 1 to n of I to the kth power. Of course, that's just equal to 1 to the k plus 2 to the k, on and on, plus n to the k. Simple enough, but it's a nice notation because it takes up less room when we write it down. We don't have to write the summation symbol with all the details that go with it. Now, when we consider S1, so this would be the sum for I raised to the first power, a summation from 1 to n. When we consider that, we're going to see that we can guess or come up with an explicit answer without a lot of problem. Here's how we'll do it. We'll write down that S1 is equal to 1 plus 2 plus 3, and we'll write out the tail of it a little more explicitly, up to plus n minus 2 plus n minus 1 plus n. Then we'll reverse the order of the terms on the right side of this equation. We'll write it down, and we'll have S sub 1 is equal to n plus n minus 1 plus n minus 2 plus all the way down to plus 3 plus 2 plus 1. Just reverse the entire right side. Now we add the two equations, and we'll align the n terms on the right side. There are n terms. We go from 1 through n. And so we're aligning them. We're adding these two equations. Well, 1s1 plus 1s1 is 2s1. 1 plus n is n plus 1. Let's write it that way. 2 plus n minus 1, well, that's again n plus 1. 3 plus n minus 2, again n plus 1. All of these terms would be n plus 1, all the way to the end here on the right, n and plus 1. How many terms are there? We've already said there are n of them. So we can simplify this to S sub 1 is equal to the explicit formula, n times n plus 1 divided by 2. So I simply noted that there are n of these terms, so adding up n of them, we can just multiply by n. And we divided by 2 on both sides of the equation. Now, this is a very simple way to find the explicit formula, but for k greater than 1, we're going to have to use a more complicated technique. And I'm going to show you a method described by I.P. Nathanson in the book, a small book he's written, Summation of Infinitely Small Quantities. And here's the method. And this is a method steps. We have several steps here for determining an explicit formula for S sub k. The first step is to start with n plus 1 to the k plus 1 and expand the binomial into an equation. The second step, create a sequence of follow-on equations by decrementing n by 1 in each succeeding equation. And this will be a little confusing until I show you examples. Step 3, add all the equations in the sequence. So the sequence came from step 2. Now we're going to add the equations to create one equation. And step 4 is to cancel common terms across the equality. And after we have done that, then we'll isolate S sub k. And we'll find that we have an explicit formula. And as I already mentioned, these steps are going to be best explained through examples. Let's start by applying the method with k equal 1. So step 1, so we need n plus 1 to the k plus 1. Well, k is 1, so we're going to get n plus 1 to the 2, or n plus 1 squared. And that's very easy to expand. It's equal to n squared plus 2n plus 1. Step 2, I want to create a sequence of follow-on equations by decrementing n by 1 in each succeeding equation. So we'll start with the n plus 1 squared equation, and then we're going to subtract 1 from all the positions that have n and all the terms that have n in them. So the n plus 1 minus 1 is just n, so we now have an n squared term on the left. On the right, for this second equation, n is above it, so now it's n minus 1 squared. We had 2n as the next term, so 2 times n minus 1 plus 1. We're going to continue with this. We'll then subtract 1 again from that equation. N minus 1 squared is equal to n minus 2 squared minus 1 plus 2 times n minus 2 plus 1. One more, n minus 3 squared is equal to n minus 2 squared is equal to n minus 3 squared plus 2 times n minus 3 plus 1. And we'd have to keep going until we reached 2 squared. So we're going to have that as the point where we stop. And we stop there because we're already going to be at 1 squared on the right side. So we stop at 2 squared on the left side, and we're at 1 squared plus 2 times 1 to the first plus 1. Okay, I want you to notice something. In this system of equations, I have a sequence of ellipses, right? The vertical ellipses. I want you to notice those. What we're doing here is constructing a meta-argument, right? I can't show you all the pieces of the argument, so I'm kind of standing above the argument and telling you that this hole here, this ellipsis, is filled in by abstracting the missing sequence of equations. And it is just an abstraction because we don't know what n is. N is general. It's a particular number, but we don't know what it is. It's not chosen. So we don't know how many additional equations we have in here. Okay, as I mentioned, we don't have a specified value for n, and we're trusting that the implied equations properly fill the gap. This is a little less than rigorous, but you'll find that when you're exercising techniques to find explicit formulas, you do things like this. You use ellipsis quite a bit and additions and things that may not be quite rigorous, but it's okay because once you find the explicit formula, you can prove it true by mathematical induction. We're now on step 3. Here we want to add all the equations in the sequence. So what you can see here is that we've now have only one equation. We've added every column has been added up, and you see the pluses in front here. So we have one equation. The left side of this equation is this n plus 1 squared plus n squared plus n minus 1 squared, all the way down to plus 2 squared. That's the left side of the equation. The right side of the equation is even more complicated. It's n squared plus 2n plus 1 plus n minus 1 squared plus 2n times n minus 1 plus 1 plus all the way down to plus 1 squared plus 2 times 1 to the first plus 1. Let's now look at the common terms on both sides of this equation. The sum from n squared to 2 to the second on the left side. If you notice this is a sum, it's just shown vertically. It's repeated in the leftmost column on the right side. You can see it here visually. There's the n squared going down to 2 to the 2 squared. On the right side, the 2 squared is not explicit. It's in the ellipsis line. But we're above the 1 squared, so that's where we stop. So these are equal terms. Step 4 is going to cancel the common terms. So it'll look like this. We're going to cancel out the n squared from both sides of the equation, the n minus 1 squared, all the way down to the 2 squared. All that gets canceled. If you look carefully at what we have now, you'll see that we have a following summary equation. On the left side, all we have is n plus 1 squared. On the right side, we have 1 squared from the bottom here, that wasn't canceled, plus going up to this column with the 2n on the top, 2n plus 2 times n minus 1 plus 2 times n minus 2, all the way down to 2 times 1 to the first, plus this column with all 1's in it. And there are n of these. There are n equations here, so these are n 1's, and that's why I have a plus n at the end of this. So you can see here horizontally I've just followed the vertical path through these equations. 1 squared plus 2n plus 2 times n minus 1 plus 2 times n minus 2 plus 2 times n minus 3, all the way to plus 2 times 1 to the first, and then plus n for all the 1's in this final column. But we can factor out this common 2 from these middle terms, and we have 1 squared plus 2 times this new term, which is just n plus n minus 1 plus n minus 2, plus going on all the way up to plus 1 to the first. And there's the plus n is still on the end. But notice something. This term, this new term, which appeared after we factored out a 2, is S1. S1 is equal to n plus n minus 1 plus n minus 2 all the way to 1 to the first. In the reverse order, normally we would write it from right to left here, 1 plus 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 all the way ending in n. But of course, by the commutative properties of addition, these are equal. So we have S1 in this equation, and we can rewrite what we have as n plus 1 squared is equal to 1 plus 2 times s sub 1, standing in for that summation, plus n. So we have a nice compact equation. Once we have this, we'll do step 5. We'll isolate sk. Well, from the previous equation, we're going to have 2s1. We're going to isolate that. So the term that was with 2s1 was, where there was an n and a plus 1. So we'll bring that across, and we'll end up with n plus 1 squared minus the term n plus 1. I've just combined them into one parentheses. Now I'm going to multiply out the squared to get n squared plus 2n plus 1, and then multiply the negative through the parentheses to get minus n minus 1. And of course we're going to get some cancellations here, and we'll have n squared plus n as our result. So at the moment we have 2 times s1 is equal to n squared plus n. But s1 is equal to n times n plus 1, the quantity, divided by 2. So let's substitute that. And so what do we end up with? We get, and I'm reminding you here, the original notation for S1 is the summation I equal 1 to n of I equal to, is equal to S1. So a transitive property tells us it's equal to n times n plus 1 divided by 2. So this is the same identity that we created earlier. We created that when we just did that simple stacking of 2 equations and then divided by 2. This was a little more complicated, but this used the general technique to get the same explicit formula. So let's try something a little more difficult. Let's try the method with k equal 2. The simpler technique wouldn't work with k equal 2. So step 1, let's start with n plus 1 to the k plus 1 and expand the binomial into an equation. K is 2, so we're starting with n plus 1 cubed. And if we multiply that out, we have n cubed plus 3n squared plus 3n plus 1. Now we're going to create the sequence of follow-on equations. We'll decrement n by 1 in all the succeeding equations until we get down to 2 squared in the left column. So here's our starting point with the n plus 1 cubed. Subtracting 1 from n plus 1, we have n. Subtracting 1 from n, we have n minus 1. So you can see what we have is n cubed is equal to n minus 1 cubed plus 3 times n minus 1 squared plus 3 times n minus 1 plus 1. It should be pretty clear what I'm doing after, see, this is the second example. We're just going to keep subtracting 1s as we create each of these follow-on equations. So the next one, we're going to have n minus 1 in the left column cubed, and then we'll have an n minus 2 in the right column. Following that, we'd have an n minus 2 in the left column, then n minus 3 in the right columns where there were factors, there were terms with n in them. We have our line of ellipsis that says we need to fill in all the way to the bottom where we have 2 cubed in the leftmost column. And in the rightmost column, we'll be at 1 cubed plus 3 times 1 squared plus 3 times 1 to the first plus 1. Step 3 asks us to add all the equations in the sequence. So again, this is now one equation. We've added all the equations, so they're in nice columns here, so we can show the additions in the columns vertically. So on the left side of the equation, we have n plus 1 cubed plus n cubed plus n minus 1 cubed plus n minus 2 cubed, all the way down to 2 cubed. On the right side, I don't want to read through all this. We can see that we have the original equation, then we add the terms with n minus 1. So we'll have the n minus 1 cubed squared into the first, then the terms with n minus 2, n minus 3, going on until we end up with 1 cubed plus 3 times 1 to the first plus 3 times 1 to the first. This was 3 times 1 to the second plus 3 times 1 to the first plus 1. There were common terms in that one, just like there were in our previous example. We cancel those out. We know that the terms in the left column, all but the first one, are common in the second column, except for this 1 cubed, which I brought up from the bottom to the top. And so here's what we have. We have n plus 1 cubed is equal to 1 cubed plus a pattern here. We have 3n squared plus 3n plus 1. Plus 3n minus 1 squared plus 3n minus 1 plus 1. You can see there's a pattern here that is following down these columns. And if you look carefully, you'll see that the following summary equation matches what we have above it. N plus 1 cubed is equal to 1, that came from 1 cubed, plus 3s2, that came from this column with the n squared. So all of these are squared terms, so that's where, and notice if I go from the bottom, we're adding 1 plus 2 plus all the way up to n minus 3, n minus 2, n minus 1, n terms all squared. So that's s sub 2. And in the next column, of course, it's 3 times n minus 1, n minus 2, etc. It's 3 times s1, right? This is the first power. We have the second power in the previous column, the first power here, so it's s1. And we have the n1s again, so plus n. Now we need to do step 5, isolate s sub k. We ended up from that last equation, 3s sub 2 is equal to n plus 1 cubed minus 3s sub 1 minus n plus 1. So we just had to bring 2 terms across the equality. Let's divide by 3. We have s sub 2 is equal to 1/3 of this expression, the n plus 1 cubed minus 3s sub 1 minus quantity n plus 1. But remember, we already have an explicit formula for s sub 1, so we can use that now and plug it in and do algebraic manipulations. I'm not going to do that here. But you could do that on your own if you wanted to. If you put in the n times n plus 1 over 2 in place of s sub 1 and ran the algebra, you should end up with this explicit expression. N times the quantity n plus 1 times the quantity 2n plus 1, all of it divided by 6. Let's do one more example, and we'll find an explicit formula for S3. And you'll see that the procedure is following this general pattern, this general method. So we're going to start with step 1, n plus 1 to the k plus 1. Well, k is now 3, so we have n plus 1 to the 4th. Well, we expand that, and you could use the binomial theorem, and get n to the 4th plus 4n cubed plus 6n squared plus 4n plus 1. Step 2, we now need to create our sequence of follow-on equations. We're going to decrement the terms with n in them, the n's. We're going to replace the n's with n minus 1, essentially, in each case. So there's the first line of the equation. The second line, we're going to have n plus 1 minus 1 is n, so s to the 4th power. And across the equality, this is the second equation, we have n minus 1 to the 4th, because we're coming from n. We have 4 times n minus 1 cubed, again coming from n, 6 times n minus 1 squared, and 4 times n minus 1 plus 1. This continues, this pattern. We're now at n minus 1 in the left column to the 4th. We'll now be at n minus 2 in all these terms across the equality on the right side. Similarly, in the next equation, we'd have n minus 2 to the 4th, and then n minus 3 to the 4th plus 4 times n minus 3 cubed, plus 6 times n minus 3 squared, plus 4 times n minus 3 plus 1. We continue on this, and this is an abstraction because we don't know what n is, so we'll say we would fill in the appropriate number of remaining equations, and of course there may not even be any. We may have run out earlier depending on what n is, but we fill in the appropriate amount because we want to get to 2 to the 4th. We want to get from n plus 1 all the way down to 2. So now we have 2 to the 4th. We want to get from n all the way down to 1. So n to the 4th, we have 1 to the 4th. And in all those cases, we want the n to be at 1. So on this bottom line, we have 4 times 1 cubed plus 6 times 1 squared plus 4 times 1 to the 1st plus 1. The next step is to add all the equations in the sequence. So when we add them, we now only have one equation left. And vertically, we're showing that on the left side, we now have n plus 1 to the 4th, plus n to the 4th, plus n minus 1 to the 4th, all the way down to plus 2 to the 4th. And on the right side, I'm not going to read all these. We have the original equation plus the original equation with n substituted as n minus 1, then another equation with of terms, another set of terms for n minus 2, for n minus 3, all the way down to till we're at 1 to the 4th, plus 4 times 1 cubed, plus 6 times 1 squared, plus 4 times 1 to the 1st, plus 1. We again cancel across the equality, and if you remember, we have common terms. Everything below n plus 1 to the 4th in the left column is left side of the equality in that column is matched by terms in the first column on the right side of the equality. And the only thing that was left in that equality is 1 to the 4th. So we still have that. The other terms are all gone. But this is what we want to build our equation from. And you're going to see that we can look carefully at this and come up with a very similar answer. N plus 1 to the 4th is equal to 1, from that 1 to the 4th, plus 4 times s sub 3. Notice we have 1 plus 2 plus plus all the way up to n, but these are all cubed. So this is, and assuming we factor out the 4, 4 times s cubed, plus 6 times s sub 2. S sub 2, because you can see that here, these are all squared terms, plus 4 times s sub 1, these are all terms to the first power, factoring out of 4, plus n. There are n ones in this far right column. We have a final step 5, isolate s sub k. Well, in this case, we had to move 3 terms across the equality, and we have 4 s sub 3 equal to n plus 1, the quantity to the 4th power, minus 6s times s sub 2, minus 4 times s sub 1, minus the term n plus 1. We can divide everything by 4, and we have s sub 3 is equal to 1/4 of this expression. I'm not going to multiply that through. I'm just going to tell you that you can remember that s sub 2 and s sub 1 can be substituted with explicit formulas. We just calculated these. S sub 2 is n times the quantity n plus 1 times the quantity 2n plus 1, all divided by 6. S sub 1 is n times the quantity n plus 1 divided by 2. Again, I'm not going to do the algebra, and after a lot of it, we're going to get this equation. S sub 3 is equal to n squared times n plus 1 squared divided by 4. So here's the explicit equation for the summation from I equal 1 to n of I cubed. Let's look for a general pattern. They all seem to have some similarity, didn't they? So n plus 1 squared is equal to 1 plus 2s times s sub 1 plus n. N plus 1 cubed is equal to 1 plus 3 times s sub 2 plus 3 times s sub 1 plus n. N plus 1 to the fourth is 1 plus 4s sub 3 plus 6s sub 2 plus 4s sub 1 plus n. Let's highlight that we have binomial coefficients here. These terms, in front of the s sub i's, are binomial coefficients. And they come from the original equations. The first one, n plus 1 squared, we have the combination of two elements taken one at a time, multiplied by s sub 1 plus n plus 1. And this one, I think I lost a plus 1. Yeah, so I lost a plus 1. Sorry about that. I'll have to put that in. And it looks like oh no, I didn't. What I did was I took the plus 1 and the n and I put them into a common term, n plus 1. So we're okay. So we have the binomial coefficient times s sub 1 plus the term n plus 1. And for n plus 1 cubed, we're going to have the binomial coefficient 3 choose 2 times s sub 2 plus 3 choose 1 times s sub 1 plus n plus 1. N plus 1 to the fourth, very similar evaluation. 4 choose 3, s cubed, 4 choose 2, s squared, 4 choose 1, s1, n plus 1. Now notice here the exponents. N plus 1 squared, the top term in the binomial coefficient is 2 from the squared. N plus 1 cubed, the top terms in the binomial coefficients are both 3. N plus 1 to the fourth, the top terms for the three binomial coefficients are all 4. And notice too that the bottom terms in the binomial coefficients match the subscripts of the s sub I. The 2 matches the 2, the 1 to 1, the 3, 3, 2, 2, 1, 1. We seem to have this result. N plus 1 to the k power is equal to k, choose k minus 1, combination, binomial coefficient, times s sub k minus 1, plus k minus 2, times s sub k minus 2, plus ellipsis, plus all the way down to k, choose 1, s sub 1, plus n plus 1. So we have a general formula for n plus 1 to the k written in terms of these summations. Okay, let's solve for the k choose k minus 1, s sub k minus 1. And we end up with n plus 1 to the k minus, and I grouped all these terms. We brought over every term except the k minus 1 term. So we have this grouping of the k choose k minus 2 times s sub k minus 2 plus k choose 1 times s sub 1 plus n plus 1. Okay, once we have that, we might want to change it a little bit. Rather than write this in terms of k minus 1, let's change it to write it in terms of k. So this formula would say I'd have the k plus 1 choose k times s to the k, s sub k, is equal to, and we're just going through here and adjusting the indexes, n plus 1 to the k plus 1 minus this term with the adjustments of k changed to k plus 1 and subtracting a 1 from the terms as they go along. We're still going to end up with 1 and n plus 1, s1 and n plus 1. This is not an easy way to generate an explicit formula for s sub k. You would have to algebraically plug in all the previous. So if you wanted to pick s sub 5, let's pick a little higher, S sub 7. Well, you're going to have to know S sub 6, S sub 5, S sub 4, S sub 3, S sub 2, all the way to S sub 1. You're going to have those explicit formulas, plug them in, and then run a bunch of algebra to create the explicit formula for S sub k. And by the way, the value of k plus 1 choose k will have to divide into what you find. Not easy, but doable. So the conclusion. I can conclude that for at least some summations, these power summations, there are methods to find explicit formulas. A deeply recursive definition is the result for these summations of integer powers, and that, because we keep recurring back on the S sub I, and it's a lot of work, but nonetheless, after a lot of algebra, an explicit formula for the summation of integer powers can be uncovered. And that's it for this lecture. Thank you.